The bell work says find the sum of all the integers from 1 to 100. That was that story of Carl Gauss. This is the exact numbers he used. He was adding 1 through 100. Yes, on the test, you can, in your calculator, go 1 plus 2 plus 3 plus 4, and anyone that does that is going to get it wrong, because it's not going to be 100, it's going to be a whole bunch, and you're going to waste a whole bunch of time. So instead, we should use that formula that the sum is going to equal the number of terms you have divided by 2. And then we're going to go ahead and do the first term plus the very last term. So that's a sub 1 plus whatever your last term is, a sub n. In this case, we're counting 1 through 100, so there are 100 individual terms. So our n would then be 100. So we'd have 100 divided by 2 times our first term, which is 1, plus our very last number, which is 100 in our sequence. And that's going to equal 50 times 101, which comes out to 50. 5,050. Scared to say it, but we got to get through it. What questions do we have from any one of our homeworks? Please tell me which number it is, like 11.2a or 11.2b, and then give me the number that I'm looking at. All right, so we have, and there are a few ways to actually do this one, so you didn't have to replicate exactly mine, but we have a plus a times r plus a times r squared plus, and then we dot, 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 we get all the way to a times r to the 10th. All right, so in short, we kind of have 11 terms. We have a times r all the way to a times r times 10. So I want to create a series, which is our summation formula. It goes from a all the way to a times r to the 10th. So the first thing I want to do is I actually want to come up with an equation that matches this sequence. I'm looking at the sequence ar squared. So that's what I'm kind of picturing in my head. I'm trying to create an explicit formula that copies this ar squared dot, dot, dot. So the explicit formula that's going to deal with that is, get rid of that. Our explicit formula is going to have a in it every single time. And then it has a times r. Every one of them has a times r squared, r. So this one right here is really r to the 0th power. So I want my very first term. So when I plug in 1 for my n, I want it to be r to the 0th power. The way we're going to do that is we're just going to take whatever my n value is, and we're just going to subtract 1 by it. Now when I plug a 1 in for this one, I have 0 for my first term. When I plug a 2 in for my second term, I have 2 minus 1, which would be r to the first. My third term would be plugging a 3 in, which would be 3 minus 1, which would be squared. Does that make sense for the explicit formula? Do you get where I'm saying, like the first term, second term? Yeah. Okay. Then we just have to have a summation formula. So my summation formula is going to be a times r to the n minus 1, where my very first term is n equals 1. I plug a 1 in, and that's my first term. Well, my very last term has to be r to the 10th power. So what does my n have to be at the very end so I can have r to the 10th power? 11. So I'm going to count from 1 to 11, and then I should get all of those out. Note, another way you could have written this, as the summation of n equals 0 to 10 of a times r to the nth. Because that would be r to the 0th, r to the first, r to the second, all the way r to the 10th. And that really would just go into changing your index. But both those worked. I think someone sent me an email whether they were okay doing that. All right, other questions on any problems from those two? Yeah, Grace. 11.23. Okay. 67. So 67, we have 1/2 plus 3/4 plus 1 plus 5/4 all the way to plus 5. Now, up until now, we needed kind of an arithmetic sequence to get the sum, right? Because we're doing a sum. That shouldn't be up there. Leave. So we should go from, let me bring this back up. So we need to, as of right now, we need to have an arithmetic sequence in order to do our sum, which means I need to know my first term, I need to know my last term, and I need to know how many numbers there are in it. So the first thing I need to recognize is what arithmetic sequence is this in order for me to get how many total numbers I have. I know I'm going 1/2 plus 3/4 plus 1 plus 5/4 plus. I need to know how many terms are in there in order to do that n divided by 2, right? We need to know how many terms are there. I already know the first term is 1/2. I know the last term is 5. I just need to know how many of those there actually are. So I'm going to come up with an arithmetic sequence for this. So in order to be an arithmetic sequence, I need to have a common difference. I need to know what we're adding by every single time. So rather than doing 1/2 plus 3/4 plus 1 plus 5/4, I'm going to create a common denominator of 4. So instead of writing 1/2, I'm going to write, how tiny was that? I'm going to write 2/4. And then my next number in the sequence would be 3/4. And then instead of 1, I'm going to write 4/4. And then we'll have 5/4, and we'll just keep going until we get to 20/4, because 20 divided by 4 is 5. Now I can see that our numerator is changing by 1 every single time. It's just going 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You could actually count it now. If you run a test and you don't know what else to do to get the number of terms, you can go, okay, 2 is 1, 3 is 4, 5, 6, 7, until you get to 20. You can count on your fingers to figure out how many terms there are. Let's not do that method. Let's instead write an arithmetic formula for this. So to do an explicit arithmetic sequence, I need to have a common difference, which is adding 1/4. We're just going to keep adding 1/4 over and over and over. Now the explicit sequence, explicit formula for this sequence would be a sub n is going to equal our first term, which is 2/4, plus our common difference, which is 1/4, times n minus 1. Well, we could reduce this down. We could actually distribute that 1/4 to get 1/4 times n. And that would be negative 1/4. So this would be plus 1/4. You aren't required to do that. Just sometimes it makes it easier. All right, now let's think about what this formula says. This formula says, if I plug in a number here, so this is our result. So if I go 2/4, this n is going to equal 1. My first term, that is what number I'm in the term. Does that make sense? So my second term is 3/4. So if I plug 3/4 in here, this n is actually going to be 2, telling me it's the second term. So what we're going to do is we're going to plug in this 20/4 into here, and it'll tell you how many terms, what term it actually is, what number term it actually is. So we're going to take that 20 divided by 4, and we're going to plug it in there. And we're going to have 20 divided by 4 equals 1/4 n plus 1/4. If you actually do this math yoga stuff, you're going to come up with n equals 19. What that n tells you is how far out that is. This is our 19th term. That means our very last term is number 19, which means there are 19 terms in this sequence. So now we can do our sum. Our sum is our n divided by 2 times our first plus our last. Do you need to see that, or are you good from there?
Yeah, I'm good.
Okay.
Thank you.
Does that make sense why I came up with this n? Remember, when I ask for the sum, you just want the first term, the last term, and how many numbers there are in there. If that means you counting it by hand, you can do that. It's much easier if you come up with an explicit formula to come up with how many terms there are in it. All right, other questions from either one of those two assignments? Mary.
On 11.2a, 39.
39. 39 says rewrite each series using the new index j as indicated, correct? Okay, so we are given a really complicated formula. We are given the summation where index I goes from 0, nope, I have the wrong one, don't I? It's n equals 2, isn't it? N equals 2 all the way to infinity. Well, that's good because I don't have to change the upper limit. And then it's 5n e to the negative 5, all divided by n factorial. And they said when I get my result, when I change my index, I actually want j equals 5. So there's one way to look at it. One way to look at it is I'm increasing my index by 3, which means I need to decrease my other side by 3. It's n minus 3 in every place that we have an n. Another way to look at it is the fact that, well, to get j equals 5, so we're starting out with n equals 2. I need to add 3 to this. I'm adding 3 to get to that 5. So this is really plus 3. Well, that means j equals whatever our n is plus 3. I take whatever my n value is, I add 3 to it, and that's going to be my j value. Well, using j equals n plus 3, we can rewrite that equation by subtracting 3 on both sides to come up with n equals j minus 3. Now what we're going to do is anytime I see an n, I'm going to replace it with j minus 3. In fact, that works right here. If I replace this n with j minus 3, I'd add 3 to both sides, and I'd come up with j equals 5. Now we're going to take this j minus 3 and plug it in for that n, and plug it in for that n, and we are pretty much done with it then. So this is going to equal, instead of 5 to the n, we're going to have 5 to the j minus 3 times e to the negative 5. All over, instead of n factorial, we'll have j minus 3 factorial. Is that a little clearer? These can be complicated. They really can, because you're like adjusting up and then the other ones are going down. I think this is sometimes the easier way to look at it, that, well, j is whatever n is plus 3, because whatever your first move is, everyone else has to boost up that 3 as well. All right, other questions on either one of the two assignments? Yeah, great. 11.2b, number 74. Uh-oh, I don't think I have this one. What is 74? Is that Jack deposit of $1,000?
No. It's the English teacher.
Okay, can I see yours real quick? Thank you. So number 74, an English teacher told her students that if they read 2n plus 1 pages of a long novel on the nth day of October for each day of October, then they will exactly finish the novel in October. How many pages are there in this novel? All right, so that means that we have an equation a sub n equals 2n plus 1. All right, that's all I needed, actually. All right, so we're getting the sum of how many pages there are. That means I need to have how many pages I read on the first day and how many pages I read on the last day, and it has to know how many total days there are. So how many days are there in October? Stole it from her. That's okay. Okay, there's 31 days in it. There's 31 days in it. And on your first day, you just have to read 2 times 1 plus 1, so that's 2 plus 1 equals 3 days. On your last day, a sub 31, you're going to have 2 times 31 plus 1, which is going to be 62 plus 1 is 63. So to get my sum, our sum of all 31 days of you reading is going to be 31 divided by 2 times 3 plus 63. And I believe that's the one I was looking for. But that's the formula, and that's the stuff we do with it. Yeah, I realized that I scratched out that problem. I think I did a different problem than I gave you. So there's a good chance a lot of us would have questions on that one. Other questions for either one of those two assignments? That's it. I really do appreciate most of you. Mr. Gerwald said most of you watched the videos and worked hard on Friday. I do appreciate those of you that actually did that. I do not appreciate the ones that he said some of you did not watch the videos and you're just online looking at the answer key to figure out how to do it. And you're going to find that out on this test. This test is historically a very low scoring test, and it's just for that reason. It's hard, so you don't do the work and you just copy answers offline. So for the couple of you that do that, don't do that. But for majority of you, thank you so much for watching that video. It makes everything so much easier for us to be able to move through this when I'm not here. All right, that means we're going to move on to today's lesson, which is geometric sequences. We have already done geometric sequences. In fact, one of the questions in class today was a geometric sequence class. We just did not put a name to it, nor did we talk about exactly how to come up with our formula for it. So it's just like arithmetic. It is just like arithmetic. You're going to go, oh, it's geometric. This is exactly how I do my explicit. This is exactly how I do my recursive without really thinking. All right, so first of all, geometric sequence is a sequence. Again, we know that. Whose consecutive terms have a common ratio. Have a common ratio. All right, so arithmetic we said had a common difference. That means you kept adding and adding and adding and adding. This is a common ratio. This is when you're multiplying, multiplying, multiplying by the same number. In fact, that's what they said R is. If you do your second term divided by your first term, that's going to equal your third term divided by your second term, which equals your fourth term divided by your third term, and so on and so forth. In other words, to get from one to another number, you need to multiply by that same number over and over again. This we're going to denote with the letter R, and R is going to be our common ratio. Remember, for arithmetic sequences, we use D for our common difference. That means we add it. When I use R, I'm talking about a common ratio, which means I am multiplying. So, some examples. Are the following geometric sequences? If so, state the common ratio. So what you're trying to do is you're trying to see, first of all, I would always check to see if it's arithmetic, because those are the easier to deal with. So I'd first go, okay, this is plus 1, plus 2, plus 4. It can't be arithmetic. All right, so we go back to the drawing board and we look, how do I get from term 1 to term 2 using multiplication? Well, that would be times 2. So this one would be times 2. 2 to get to 4 would be times 2. And 4 to 8 would also be times 2. Since you are multiplying by the same number over and over and over, it is in fact geometric. It is always geometric if you're multiplying by the same number over and over. So this is going to be your sign that this is geometric. And not only is it geometric, we also know our R, our common ratio, is 2. So that stands for my common ratio. So it's geometric, common ratio, 2. Not that much different than arithmetic, except it has a multiplication sign instead of a plus or minus sign. Don't use division. All right, always try to use multiplication. Don't go, okay, because some of these will count down. It'll go like 4, 2, 1, 1/2. Don't go, I'm dividing by 2. Go, you're multiplying by 1/2. Always go with multiplication so you can come up with your common ratio. So always look for multiplication. All right. Our next one, we have 1/2, then we have 1/8, then we have 1 over 32, then we have 1 over 128. Well, to get from 2 to 8, we multiply by 4. To get from 8 to 32, we multiply by 4. To get from 32 to 128, we multiply by 4. you could say your common ratio in your denominator is 4. But sometimes it's easier to leave it as your exact fraction. That to get from 1/2 to 1/8, you're going to multiply by 1/4. To get from 1/8 to 1/32, we'd multiply by 1/4. And finally, we would multiply by 1/4. So since we're multiplying by the same number, it is in fact geometric. With a common difference of r equals 1/4. It's not hard on this one, but sometimes it's hard to know what you're multiplying by or what to even check to multiply by because it'd be really weird fractions. So what can really help you is note. We'll do a note. Sometimes you can find your geometric sequence by doing your second term divided by your first term, which would equal 1/4. So sometimes you have really complicated ratios that you can't find your common ratio, at which point you can just use your second divided by first. Okay, that's by 1/4, and then try multiplying all of them by 1/4. Sometimes they be really complicated decimals, really complicated fractions. So sometimes it's just nice to know, okay, my second term divided by first term, what does that equal? All right, I'm going to try multiplying it all by that number to see if it has a common ratio. All right, well, that's it. That's what you're looking for geometric. As soon as you know it's geometric, you can come up with two different formulas. You can come up with a recursive, and you can come up with an explicit. Well, recursive, the first thing we're going to do with recursive is we're going to state what our first term is. We don't know what it is, so we'll just put x. And then our recursive is going to be a sub n equals. Well, for arithmetic, it was the term before it plus a number. This is pretty much the same. We're going to do the term before it and multiply it by a number rather than adding. So we're going to go r times the term before it, which is a sub n minus 1. You just take the term before and you multiply it by that number. The explicit isn't so bad either. Oh, I didn't miss any notes, did I? I did not. Okay, our explicit isn't so bad. It turns out it's just an exponent. It is a sub n equals. Now, just like kind of arithmetic, you have to know what your first term is. You have to know where you're starting. So this will be a sub 1. And then we're going to multiply that by r to the n minus 1. So it's just like arithmetic that you have to know your first term and your common ratio. For arithmetic, you need to know your first term and your common difference. Once you have those two things, you know your recursive and you know your explicit. All right, let's do an example of listing your first 4 terms. Now, right here, I know it is geometric. Anything with to the power, like to the power of n, means it's going to be geometric. So our first 4 terms of a sub n equals 3 to the n would be a sub 1 equals 3 to the first, which just equals 3. My second term would be 3 squared, which would be 9. My third term would be 3 to the third, which is going to equal 27. And a to the fourth is going to be 3 to the fourth, which is going to be 81. I do want to note, though, that this is definitely geometric, because this is times 3, this is times 3, and this is times 3. So in your calculator, you could just keep hitting multiply by 3, and you'd get your next few terms. Our next one is also geometric because it's to the power of n minus 1. Anything to the power of n minus 1, n plus 2 is automatically going to be geometric sequence, which is nice to know because this is slightly harder to plug in your calculator until you realize the pattern. So let's go ahead and do our first term. My first term equals 100 times 1/2 to the 1 minus 1 is 0. Anything to the 0th power is 1, so that's 100 times 1, which would just give me 100. All right, my second term is going to be 100 times 1/2. 2 minus 1 is 1. So that's 100 times 1/2, which is 50. Now, if you realize that this is geometric, and you realize that I'm just dividing by 2, I'd multiply the next one by 1/2, multiply by the next one by 1/2, multiply by the next one by 1/2. However, if you don't recognize that pattern, you do have to just keep going. A sub 3 would be 100 times 1/2 squared, because it's 3 minus 1. 1/2 squared is 100 times 1/4, which is 25. Once again, it's just multiplying by 1/2. That's 1/2 times 1/2. So if we did a sub 4 is going to equal 100 times 1/2 to the third power. That is going to be half of 25. I didn't miss anything? No. So we have 12.5. All right. Our next one should be actually coming up with the formula, right? A formula for general term of each geometric sequence. You just need your first term, and you need to have your common ratio. I believe I have it worded as I wanted it. I just want to make sure I didn't add anything else to it. I just want the explicit formula. Yeah, I just want the explicit formula. Anytime you see this general term, that specifically means I just want an explicit formula. In fact, if I ever ask for one formula and I don't specify, I always want explicit. If I want recursive, I will specifically say recursive. If I want 2 equations, I will specifically say do 2 equations. Explicit is the most important. Recursive is not needed as much. Explicit is probably your most formula to come up with. All right, so we're supposed to first determine if it's geometric sequence. So if I do 0.3 to 0.03, well, I'm moving 1 decimal place down. So I must be multiplying by either 0.1 or 1 over 10. To go from 0.03 to 0.003, we'd multiply by 1 over 10. And finally, we'd multiply by 1 over 10 again, which means, in fact, it is geometric. I told you it's geometric, but it's always a good idea to check. It is geometric where your common ratio equals 1 over 10. Most important part are your first term and your common ratio. All right, as soon as we have those two things, we can go ahead and write our formula. Our explicit formula is a sub n equals our first term, which is 0.3, times our r, which is 1 over 10 to the n minus 1. Once again, this is my first term. This is my common ratio, and it's just to the n minus 1 power. Remember we did arithmetic sequences? And we alternated between -1 and 1. We had to use -1 to the n or -1 to the n minus 1. You can forget that with geometric sequences. Geometric sequences, you can multiply by a negative number. Your r can be a negative number. So if I do 2 times a -3, you come up with -6. Times a -3, you come up with a positive 18. Alternating between positive and negative on a geometric sequence just means that your r value is going to be negative. The only time you have to use -1 to the n or n minus 1 is for arithmetic sequences. Pay attention to what I'm saying because this is missed on the test a lot. For geometric sequences, when it alternates between positive and negative, it just tells you your common ratio is a negative number. For arithmetic, when it alternates between positive and negative, you have to use that -1 to the n or -1 to the n minus 1. So arithmetic, you have to come up with that -1. For geometric, you don't have to worry about it. Your r value is going to take care of that alternating between negative and positive. So if I'm checking, well, to get from 2 to 6, you have to multiply by 3. From 6 to 18, I multiply by 3. From 18 to 54, I multiply by 3. To handle that alternating, it better be by a -3. So 2 times a -3 is negative 6. Negative 6 times a negative 3 is going to be a positive 18. And finally, multiply by a negative 3 again, you come up with a negative 54. Those are terribly written. I should probably put parentheses, otherwise it looks like x minus 3. It's times negative 3 times negative 3. Are we all clear on that, what I'm looking for alternating between negative and positive? You have to decide if it's arithmetic or geometric. It depends on how you take care of it. So with geometric, it's a lot easier because our r equals a negative 3. Our formula is going to be a sub n times our first term times our r to the n minus 1. Once again, we just need to know our first term, and I need to know what my common ratio is. So geometric in that sense is a lot easier than arithmetic. In fact, geometric generally have the easier formulas. They look harder, but they're a lot easier to plug in. You don't have to worry about it happening in the denominator or the numerator. You don't have to worry about that negative 1 to the n. So in that respect, geometric's a lot easier. Just find your first value and your r, and it takes care of itself. All right, keep on plugging through. We have 6, 8, 10, 12. Is that geometric? What is that sequence? 6, 8, 10, 12. If it's not geometric, it is, yep, arithmetic. It doesn't mean it has to be one or the other. It could be 6, 8, 11, 13, where it just doesn't make a pattern. But this would be, in fact, arithmetic. This would be plus 2, plus 2, plus 2, which means it's arithmetic. Does anyone else think it should just be called arithmetic? But they had to delineate that we're not doing arithmetic, we're doing arithmetic. All right, our next one is 1/2, 1 over 6, 1 over 18, 1 over 54. So I just look at that 2, 6, 18, and 54, and I look for a number if it works. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. Now to keep it as a fraction, it's just going to be times 1 over 3. Times 1 over 3. Times not 1/2, but 1 over 3. We have our r value. It is geometric because we are multiplying over and over and over again. So we are just going to have our formula equals our very first term, which is 1/2, times our r value to the n minus 1. So I do like geometric in this sense that you don't have to think very much about it. Arithmetic, sometimes you do, because sometimes it's just happening in the numerator, it's just happening in the denominator, you're adding by 2. For geometric, those are probably your easier ones to come up with. It is just always your first term and your common ratio. You don't have to do much thinking about it. If you're thinking past that, it means you're doing too much work. You're trying to put it as an arithmetic sequence. All right, continuing on. The next one says, find the first 4 terms of each sequence and determine if the sequence is geometric. I, in fact, already know that first one is a geometric sequence. It is negative 2 to the nth power. I know it's 3 times n, but it is to the nth power. In fact, you could rewrite this. You could rewrite this as, well, negative 2 to the third would be 2 times 2, which is 4, times 2 is 8, and it'd be negative. You could rewrite this as negative 8 to the nth power. So in fact, this is a geometric sequence that you're multiplying by negative 1/8. But let's pretend like we didn't do that, and we are actually going to do the whole setup to see if it's true. So if I had to do my first term, I'd do b sub 1 equals negative 2 to the 3 times 1, which would be 3. Oh, we're not doing that one. Cool. Which is going to equal a negative 1/8. My second term would be negative 2 to the 3 times 2, which would be to the 6th, which is going to equal a positive 64. Which follows this. I'm multiplying by a negative 8. To get to my third term, we would do negative 2 to the 3 times 2, which would be, 3 times 3, which would be to the 9th, If you plug that in your calculator, you're going to come up with a negative 512. And finally, b sub 4 would equal negative 2 times 3 times 4. So that would be to the 12th. And you come up with a positive 496. All of these are just multiplying by a negative 8. So if you're ever on the test and I said, is it geometric or arithmetic, and you notice it's to the nth power, anything, 3n minus 1, something like that, you can automatically know it's geometric. It has some kind of multiplication in it. That's what an exponential function is. An exponential function is geometric by nature. Our next one I'm going to recognize as being geometric before I even do it as well. It is negative 2 times the term before it. So you're constantly taking the term before it and multiplying it by a negative 2. That is the definition of geometric as well. So our first term, let's go back to black. Our first term equals 1.25. Our second term would be 1.25 times a negative 2. Maybe I should put that negative 2 up front, actually, just like we did. So it's negative 2 times the term before it, which is 1.25, which is going to be a negative 2.5. Then our third term is going to equal a negative 2 times the term right before it, which would be negative 2.5. Which is going to equal a positive 5. And then you'd find out your last one is, in fact, a negative 10. So that is, in fact, geometric. You are multiplying by negative 2 over and over again. So both of these two were geometric. Our last one is c sub n equals 3n. My first term would be c sub 1 would be 3 times 1, which would equal 3. C sub 2 would be 3 times my n, which is 2, so it would be 3 times 2, which would be 6. C sub 3 would be 3 times 3, which is 9. And C sub 4 would be 3 times 4, which would equal 12. This is arithmetic. You are adding 3 over and over and over. This one would be arithmetic. And that would be because you're adding 3. All right, questions on that? All right.